In 1936, when engineers at Supermarine presented the first sketches of what would become the Spitfire, the meeting room erupted in protests. Designer R.J. Mitchell had proposed something that seemed like technical suicide: elliptical wings, a shape that had never been used on fighter aircraft. Experts said it would be impossible to manufacture, far too expensive for mass production, and structurally risky. Mitchell, already battling terminal cancer, knew he had no time for endless debates. He simply said, "Build it." 3 years later, when the Luftwaffe crossed the English Channel in September 1939, Europe stood on the brink of collapse. The Nazi war machine seemed unstoppable. France fell in 6 weeks. Poland was crushed in days. And now, the skies over England were about to decide the fate of the free world. It was then that the Spitfires, with their ridiculous elliptical wings, rose to face the German Messerschmitts. What German engineers hadn't expected was that this impossible design reduced aerodynamic drag so efficiently that the Spitfire could turn faster, climb higher, and outperform its adversaries in close combat. The Battle of Britain in 1940 became the ultimate proving ground. RAF pilots reported achieving maneuvers that would be fatal in other aircraft. The elliptical wings distributed lift so evenly that the aeroplane responded like an extension of the pilot's own body. For the first time, the Luftwaffe encountered real resistance. Hermann Göring, commander of the German Air Force, was furious to discover his losses exceeded the British. Hitler was forced to cancel Operation Sea Lion, the planned invasion of England. The design everyone called madness had saved a nation. Across the Atlantic, American engineers faced their own skeptics. When Clarence Kelly Johnson proposed a twin-engine fighter with a twin-boom tail design for Lockheed, they said it would be too heavy, too complex, too risky. But the P-38 Lightning that emerged from his drawing boards broke every record for speed and range. Meanwhile, in Germany, secret teams worked on something even more radical: swept-back wings that would allow supersonic speeds. The Messerschmitt Me 262, the first operational jet fighter in history, flew in 1944 with this impossible technology. The Second World War wasn't won solely by soldiers in trenches or tanks on battlefields. It was won at 10,000 meters altitude by men who dared to challenge conventional thinking. Each of these ridiculous innovations cost careers, reputations, and countless hours of testing. Mitchell didn't live to see his Spitfire save England. He died in 1937. But his legacy flew in every mission, every combat, every pilot who returned home because those elliptical wings gave him the extra seconds needed to survive. The war proved an inconvenient truth for engineering conservatives. Sometimes the impossible is merely the inevitable waiting for someone brave enough to try. The story of aviation's most revolutionary designs during the Second World War begins not in the skies, but in the drafty offices and experimental hangars where men with slide rules and dreams fought battles as fierce as any aerial dogfight. In the mid-1930s, the world was recovering from one global catastrophe and sleepwalking towards another. The Great War had demonstrated that aeroplanes could be weapons, but they were still relatively primitive machines, fabric-covered frameworks that could barely exceed 200 miles per hour. Reginald Joseph Mitchell was not a typical aircraft designer. Born in 1895 in Stoke-on-Trent, the heart of England's pottery country, he had trained as an engineer in locomotive works before finding his way to the Supermarine Aviation Works in Southampton. By the early 1930s, he had already made a name for himself designing seaplanes that won the prestigious Schneider Trophy races, pushing the boundaries of speed with sleek, innovative designs that looked more like racing cars with wings than traditional aircraft. But Mitchell knew that racing seaplanes and combat fighters were entirely different beasts. The Air Ministry specifications that landed on his desk in 1934 were demanding almost to the point of absurdity. They wanted an aircraft that could exceed 300 miles per hour, climb to 15,000 feet in under 7 minutes, carry 8 machine guns, and still be maneuverable enough to engage in the violent ballet of air combat. Most designers would have compromised, accepting that you couldn't have everything. Mitchell refused to compromise. The challenge lay in the wings. Traditional aircraft wings of the era were essentially rectangular or slightly tapered, straightforward to build and structurally sound, but they were also draggy, creating turbulence at the tips and wasting precious energy that could be converted into speed or maneuverability. Mitchell had become obsessed with efficiency during his racing seaplane days. He understood that in the air, every ounce of drag was an enemy, every wasted horsepower a potential death sentence for a pilot facing superior numbers. The elliptical wing wasn't Mitchell's invention from whole cloth. The concept had theoretical advantages that aerodynamicists understood on paper. An ellipse distributes lift most efficiently along the span, reducing induced drag to its theoretical minimum. But theory and practice are separated by a chasm of engineering challenges. No one had successfully built an elliptical wing for a high-performance fighter because the manufacturing difficulties seemed insurmountable. When Mitchell presented his proposal, the reaction was immediate and hostile. Production engineers looked at the complex curves and compound angles and saw a nightmare. Each wing would need to be built with dozens of different ribby shapes, each one unique. The supporting structure would require precision manufacturing far beyond what most factories were equipped to handle. In an era when aircraft were still built more like furniture than machines, with craftsmen working by hand, the elliptical wing seemed like an engineer's fantasy that would bankrupt any company foolish enough to attempt it. The Air Ministry evaluators were hardly more encouraging. They worried about structural integrity under combat stress. Would these elegant curves hold together when a pilot pulled maximum G-forces in a desperate turn? What about battle damage? A hole in a conventional wing was manageable, but would damage to these complex structures lead to catastrophic failures? And then there was the cost. Not just in money, but in time. Britain's military planners could see war coming. They needed fighters, and they needed them quickly. An experimental design that might take years to perfect seemed like a dangerous luxury. Mitchell was dying, though few knew it at the time. He had been diagnosed with cancer, and the prognosis was grim. Perhaps this knowledge fueled his determination, or perhaps it simply clarified his priorities. He had spent his entire career building towards this moment, this aircraft. He would not compromise his vision for bureaucratic convenience or engineering timidity. In meeting after meeting, he defended his design, not with passion, but with relentless logic and data from wind tunnel tests that showed undeniable advantages. The Supermarine board faced a critical decision. Supporting Mitchell meant investing enormous resources in an unproven concept. The company could go bankrupt if the project failed, but Mitchell had never failed before. His Schneider trophy racers had dominated international competition. His reputation was sterling. Eventually, almost against their better judgment, they authorized him to proceed. The prototype would be built. Throughout 1935 and 36, the aircraft that would become the Spitfire took shape in Supermarine's Southampton factory. Skilled craftsmen wrestled with the complexities of the elliptical wing, developing new techniques and tools as they went. Each rib had to be precisely shaped, each spar carefully fitted. The fuselage was equally revolutionary, a monocoque structure where the skin itself carried structural loads, saving weight whilst increasing strength. Mitchell supervised every detail, driving his team hard but never asking for anything he hadn't carefully calculated and tested. The first flight came on the 5th of March, 1936. Test pilot Joseph "Mutt" Summers took the prototype into the air from Eastleigh Aerodrome near Southampton. The flight lasted just 8 minutes, but when Summers climbed out of the cockpit, his assessment was characteristically brief. "I don't want anything touched." From a test pilot who made his living finding flaws, this was extraordinary praise. The Spitfire worked, and it worked brilliantly. But Mitchell would not see his creation enter service. The cancer that had been gnawing at him throughout the design process finally claimed his life on the 11th of June, 1937. He was just 42 years old. The first production Spitfires were still months away from delivery to RAF squadrons. Mitchell died not knowing whether his elliptical wings would prove themselves in the crucible of combat, whether his obsessive pursuit of perfection would save lives or prove to be an expensive folly. As Mitchell's Spitfire moved from prototype to production in the late 1930s, the political situation in Europe deteriorated with terrifying speed. Adolf Hitler had torn up the Treaty of Versailles and embarked on a massive military expansion. The Luftwaffe, officially non-existent just a few years earlier, was rapidly becoming the most formidable air force in the world. German engineers, freed from the constraints of the treaty that had ended the Great War, were developing advanced aircraft that made many existing Allied fighters look obsolete before they even entered service. The challenge facing Britain's aircraft industry was immense. The Royal Air Force had been neglected during the lean years of the Depression, and now suddenly needed to expand from a few dozen squadrons to a force capable of defending the entire nation. The Air Ministry placed orders for hundreds of fighters, but the Spitfire's complex construction created a bottleneck. Factories that could stamp out simpler designs by the dozen found themselves struggling with the precision required for elliptical wings. Supermarine and its parent company Vickers worked frantically to expand production capacity. New factories were built, workers were trained in the specialized techniques required, and gradually production rates increased. But there was another problem that Mitchell had never lived to address. The Spitfire's revolutionary design made it difficult to modify and upgrade. As the war approached and new requirements emerged, demanding heavier armament, greater fuel capacity, and more powerful engines, engineers discovered that the beautifully optimized structure had little margin for change. This created fierce debates within the Air Ministry and RAF. Some argued that Britain should focus on simpler, easier-to-build fighters like the Hawker Hurricane, which used traditional construction methods and could be produced in greater numbers. The Hurricane had a fabric-covered fuselage and conventional wings, making it much easier to repair and modify. It could also be manufactured by smaller workshops and repair facilities that lacked the precision equipment needed for Spitfires. In a long war of attrition, perhaps quantity would matter more than quality, but others recognized that the Spitfire represented something more than just another fighter. It was a statement of British engineering excellence, proof that innovation and technical sophistication could trump brute force industrial capacity. More importantly, early combat trials and evaluations showed that in skilled hands, the Spitfire was simply superior to anything else flying. The elliptical wings gave it a rate of roll and turn performance that pilots described as almost supernatural. In aerial combat, where victory or defeat could be measured in fractions of a second, this advantage was potentially decisive. The argument became moot when Germany invaded Poland on the 1st of September, 1939. 2 days later, Britain and France declared war. The long-dreaded conflict had begun. Fighter Command, led by Air Chief Marshal Hugh Dowding, had just over 30 RAF squadrons, including only 9 equipped with Spitfires. The majority still flew Hurricanes or even older biplanes. Against them, the Luftwaffe could field more than 1,000 modern fighters. The odds were sobering. The first months of the war, the period that became known as the Phony War, saw relatively little aerial combat over Western Europe. German forces concentrated on Poland, and then prepared for operations in Scandinavia. This breathing space allowed Fighter Command to continue training and re-equipping. More Spitfire squadrons became operational, and pilots began to truly understand the capabilities of their machines. They discovered that the elliptical wing wasn't just about speed or maneuverability in isolation, but about harmony, the way all the aircraft's characteristics worked together. Flight Lieutenant Alan Deere, a New Zealand pilot who would become one of the RAF's leading aces, later described his first flights in a Spitfire as revelatory. Previous fighters felt like machines that had to be wrestled and forced to do what you wanted. The Spitfire responded to the lightest touch, anticipating the pilot's intentions. In a climbing turn, where conventional fighters would shudder and lose energy, the Spitfire seemed to dig its wings into the air and pull itself upward. This wasn't magic, it was physics. The result of Mitchell's elliptical wings distributing lift so efficiently that the aircraft could perform maneuvers that should have been impossible. Then, in May 1940, the Phony War exploded into terrifying reality. Germany launched its blitzkrieg against France and the Low Countries. Panzer divisions smashed through the Ardennes, bypassing the Maginot Line and racing towards the Channel coast. The Luftwaffe swept Allied air forces from the skies with brutal efficiency. France, which had fielded the largest army in Europe, collapsed in just 6 weeks. British forces barely escaped annihilation at Dunkirk, leaving behind virtually all their heavy equipment. By late June, Britain stood alone against the Nazi juggernaut. Hitler and his generals assumed Britain would negotiate peace. Instead, Winston Churchill, who had become Prime Minister during the crisis, gave his famous speeches about fighting on the beaches and never surrendering. This defiance created a problem for Hitler. He couldn't invade Britain whilst the RAF controlled the skies over the Channel. His army had conquered most of Europe, but 20 miles of water might as well have been an ocean without air superiority. The stage was set for the first major battle to be fought entirely in the air. Reichsmarschall Hermann Göring, commander of the Luftwaffe, was supremely confident. His forces had destroyed the air forces of Poland, France, and the Low Countries with contemptuous ease. He commanded over 2,000 aircraft, including roughly 1,200 bombers and about 1,000 fighters. Against this armada, Fighter Command could muster just over 600 operational fighters, of which only about 300 were available at any given moment, due to maintenance and pilot rest requirements. Göring boasted that he would sweep the RAF from the skies in a matter of days. What Göring didn't fully understand was that this battle would be fought on Britain's terms, over Britain's territory, using a defensive system that was itself revolutionary. Air Chief Marshal Dowding had spent years developing an integrated air defense network that combined radar stations along the coast, observer corps inland, fighter control centers, and radio-equipped fighters. This system meant that British fighters didn't have to fly standing patrols, burning fuel and exhausting pilots. They could wait on the ground until radar detected incoming raids, then be vectored precisely to intercept. The battle began in earnest in July 1940 with attacks on Channel convoys and coastal targets. German planners believed these raids would force Fighter Command to commit its forces to defensive battles where superior German numbers would grind them down. For the RAF pilots, these early encounters were their first real test against the Luftwaffe's best. The Messerschmitt Bf 109, Germany's premier fighter, was a formidable opponent, faster in a dive and with a better rate of climb than either the Spitfire or Hurricane at certain altitudes. But in turning combat, something extraordinary happened. Pilots discovered that the Spitfire could outturn the Messerschmitt at almost any speed. Those elliptical wings, the design that had caused so much controversy, proved their worth in the most brutal way possible. In a dogfight, when a Spitfire and a Bf 109 entered a turning battle, the Spitfire could gradually pull its nose around to a firing position. German pilots, accustomed to dominating opponents, found themselves on the defensive, forced to dive away and disengage rather than fight it out. Squadron leader Bob Stanford Tuck, who would end the war with nearly 30 confirmed victories, described combat in a Spitfire as almost unfair. He recounted an engagement where he had locked onto a Messerschmitt's tail and simply held the turn, watching his deflection angle decrease steadily as his tighter turning circle brought his guns to bear. The German pilot, undoubtedly skilled and experienced, tried every trick, but the physics were inexorable. Mitchell's wings were doing exactly what his calculations had predicted, creating more lift with less drag, allowing the Spitfire to maintain energy in maneuvers that bled speed from other aircraft. As the battle intensified through August, the Luftwaffe changed tactics. Göring ordered massive raids against RAF airfields and aircraft factories, intending to destroy Fighter Command on the ground if he couldn't defeat it in the air. Hundreds of bombers, escorted by fighters, droned across the Channel daily. The skies over southern England became a chaotic battlefield, where dozens of individual combats merged into swirling furballs of aircraft, tracer fire, and falling machines. The strain on Fighter Command was immense. Pilots flew 4 or 5 sorties a day, climbing to altitude, fighting desperately for 10 or 15 minutes, landing to refuel and rearm, then doing it all again. Many were teenagers, barely out of training, thrust into combat where mistakes meant death. The casualty rate was appalling. Squadrons that started the day at full strength might lose a quarter of their pilots by nightfall. Ground crews worked around the clock repairing damaged aircraft, patching bullet holes, replacing shattered canopies, doing whatever it took to keep fighters airworthy. In this crucible, the differences between the Spitfire and Hurricane became clear. The Hurricane, built with older construction methods, was easier to repair. Bullet holes in its fabric-covered fuselage could be patched quickly. It was also a steadier gun platform, making it effective against bombers. But in combat with German fighters, Hurricane pilots were at a disadvantage. The Spitfire's performance edge, modest on paper, became magnified in combat. A 5-mile-per-hour speed advantage could mean the difference between catching a fleeing enemy or watching him escape. A slightly better turn rate could mean getting your guns on target or becoming the target. Doubting, pragmatic and ruthlessly focused on winning rather than glory, deployed his forces accordingly. Hurricane squadrons were directed primarily against bomber formations, where their steady gun platforms and rugged construction were most valuable. Spitfire squadrons were tasked with engaging the German fighter escorts, keeping them away from the Hurricanes and bombers. This division of labor maximized the strengths of both aircraft and became standard Fighter Command doctrine. The crisis came in early September. Fighter Command was on the ropes, losing pilots faster than they could be replaced. Experienced flight commanders, the men who held squadrons together and taught newcomers how to survive, were being killed or wounded at an unsustainable rate. Some airfields had been so badly damaged that squadrons had to relocate. A few more weeks of this attrition and doubting would run out. Of trained pilots, even if he had aircraft to spare. Britain was losing the battle. Then Hitler made a catastrophic mistake. Enraged by RAF bombing raids on Berlin, he ordered the Luftwaffe to shift from attacking airfields to bombing London and other cities. Göring, eager to unleash his bombers on what he saw as a terror campaign that would break British morale, complied enthusiastically. On the 7th of September, over 300 bombers escorted by 600 fighters attacked London in broad daylight. The Blitz had begun. For Fighter Command, this was an unexpected reprieve. The pressure on airfields eased immediately. Damaged bases could be repaired. Exhausted squadrons could be rotated to quieter sectors for rest. New pilots could receive a bit more training before being thrown into combat. More importantly, the German shift to city bombing played directly to British strengths. Deep raids on London meant German fighters were operating at the extreme edge of their range, with only minutes of combat fuel before having to turn back. Spitfires and Hurricanes, fighting over their own territory, could engage at full throttle without worrying about having enough fuel to reach home. The battle reached its climax on the 15th of September, a date now celebrated as Battle of Britain Day. The Luftwaffe launched 2 massive raids on London, throwing virtually everything it had into what Göring promised would be the knockout blow. Fighter Command met them with every available aircraft. The skies over southern England filled with hundreds of aircraft in the largest aerial battle yet seen in history. Spitfires and Hurricanes tore into the bomber formations whilst German fighters tried desperately to protect their charges. When the day ended and both sides tallied their losses, a shocking reality emerged. The Luftwaffe had lost nearly 60 aircraft destroyed and many more damaged. Fighter Command's losses were less than 30. More importantly, British pilots who bailed out over England could be back in combat the next day. German air crews who survived being shot down became prisoners. The exchange rate was unsustainable for the attackers. Göring had promised Hitler air superiority, but instead his vaunted Luftwaffe was being bled white. Across the Atlantic Ocean, American military observers watched the Battle of Britain with intense interest. The United States was officially neutral, but President Franklin Roosevelt and many in the American military establishment understood that neutrality might not last. If Britain fell, the United States would face a world dominated by hostile totalitarian powers. The performance of British fighters, particularly the Spitfire, provided valuable lessons for American aircraft designers racing to develop the next generation of combat aircraft. Among those designers was a 30-year-old engineer named Clarence Leonard Kelly Johnson. Born in Ishpeming, Michigan, the son of Swedish immigrants, Johnson had clawed his way out of poverty through brilliance and relentless determination. Poor eyesight had disqualified him from becoming a military pilot, the dream of countless young men of his generation, but it hadn't stopped him from becoming one of the most innovative aeronautical engineers of his era. By 1940, he was working for Lockheed Aircraft Corporation in California, already developing a reputation for unconventional thinking. The Army Air Corps had issued a requirement for a full high-altitude interceptor capable of catching and destroying enemy bombers before they reached their targets. The specification called for extreme performance, speed over 400 miles per hour, and the ability to operate effectively above 30,000 feet. Most manufacturers proposed conventional single-engine designs, essentially scaling up existing fighters with more powerful engines. Kelly Johnson looked at the numbers and concluded that a single engine couldn't deliver what was needed. He proposed something radical, a twin-engine fighter. The reaction from Army evaluators and Lockheed's own management was skeptical, bordering on hostile. Twin-engine fighters had been tried before and generally failed. They were heavy, reducing maneuverability. They were complex, increasing maintenance requirements. They were expensive, limiting production numbers. Every piece of conventional wisdom said that fighters should be light, simple, single-engine aircraft. Johnson's proposal seemed to violate every principle of fighter design. But Johnson had done his calculations. 2 smaller engines, he argued, could deliver more total power than 1 large engine whilst providing redundancy. If one engine was damaged, the pilot could potentially make it home on the other. The twin-engine layout also allowed for a different structural approach. Instead of a conventional tail, Johnson proposed twin booms extending back from the engines, with the tail surfaces mounted between them. This layout allowed for a very heavy concentration of guns in the nose, all firing directly forward without the synchronization problems of firing through a propeller arc. The design that emerged from Johnson's team was like nothing else flying. The Lockheed P-38 Lightning, as it was designated, looked almost alien with its twin-boom layout, tricycle landing gear, and counter-rotating propellers. When the prototype first flew in January 1939, it immediately shattered the conventional wisdom that had dismissed twin-engine fighters. On its 5th flight, test pilot Ben Kelsey attempted a coast-to-coast speed record, racing from California to New York in just over 7 hours with stops for refueling. The attempt ended in a crash landing short of the airport, but the point was made. The Lightning was blindingly fast. Production P-38s began reaching Army Air Forces squadrons in late 1941, just as America's neutrality was shattered by the Japanese attack on Pearl Harbor. The Lightning would go on to become one of the most versatile and successful American fighters of the war, but its development path illustrated the same lesson as the Spitfire. Revolutionary designs faced enormous resistance from conventional thinking. Both Mitchell's elliptical wings and Johnson's twin-boom layout were initially dismissed as impractical. Both proved their skeptics catastrophically wrong. The Lightning faced particular challenges in the European theater. At the extreme altitudes where heavy bombers operated, early P-38s encountered problems with engines and cockpit heating that plagued operations. But in the Pacific and Mediterranean, the Lightning's long range and heavy firepower made it devastatingly effective. American aces like Richard Bong and Thomas Maguire flew Lightnings to become the highest-scoring American fighter pilots of the war. The same characteristics that made skeptics doubt the design, twin engines, complexity, and unconventional layout, became advantages in skilled hands. Meanwhile in Britain, the Spitfire continued to evolve in ways Mitchell could never have imagined. The original design had been optimized around the Rolls-Royce Merlin engine, producing just over 1,000 horsepower. As the war progressed and German aircraft improved, supermarine engineers faced constant pressure to increase performance. They fitted more powerful Merlin variants, then switched to the Rolls-Royce Griffin engine producing over 2,000 horsepower. They strengthened the wings to carry heavier weapons and more fuel. They modified the elliptical wingtips to improve high-altitude performance. Each modification created new challenges. The beautiful elliptical wing that had caused so much controversy in the 1930s was now almost sacred, but it had been designed for a much lighter aircraft with less powerful engines. Engineers worried constantly about structural limits. Test pilots pushed modified Spitfires through grueling trials, diving at speeds that approached the sound barrier, pulling G-forces that threatened to tear wings off, simulating combat damage to verify that the structure could take punishment and survive. What emerged was a testament to the fundamental soundness of Mitchell's original concept. Despite nearly doubling in weight and power over the course of the war, the basic Spitfire design remained viable and competitive. The elliptical wing adapted to roles Mitchell never envisioned: low-level photo reconnaissance, high-altitude interception, ground attack, carrier operations. The elegant curves that had seemed like an expensive indulgence in 1936 proved to be the foundation of the most successful British fighter program of the war. By 1942, as the tide of war slowly began to turn against Germany, the Luftwaffe faced Spitfires over North Africa, Malta, and the occupied territories of Western Europe. German pilots who had been dismissive of British fighters in the early days of the war developed grudging respect for the Spitfire. In combat reports and diaries, they noted its maneuverability and the skill of RAF pilots who had survived years of combat. The easy victories of 1940 were long gone. Whilst Britain and America developed their revolutionary fighters through a combination of individual genius and democratic debate, Germany's approach to aviation innovation was fundamentally different. The Nazi regime's centralized control allowed for massive resource allocation to favored projects, but also created fierce rivalries between designers and companies competing for Hitler's favor. This environment produced both brilliant innovations and catastrophic wastes of resources, sometimes in the same project. By 1942, perceptive German engineers recognized that piston engine fighters were approaching their practical limits. Engines were becoming so powerful and complex that diminishing returns had set in. The future, they believed, belonged to jet propulsion. Several German companies had been experimenting with jet engines since the late 1930s, and now these projects received urgent priority. The potential advantages were enormous: speeds of 500 miles per hour or more, altitudes where piston engine fighters couldn't operate, and the ability to overwhelm existing Allied fighters. But jet engines created aerodynamic problems that didn't exist with slower aircraft. As aircraft approached the speed of sound, airflow over the wings began to behave differently. Shock waves formed, creating tremendous drag and control problems. Conventional straight wings that worked perfectly well at 300 miles per hour became liabilities at 500. German aerodynamicists, building on research that dated back to the 1920s, understood that swept wings angled back from the fuselage rather than perpendicular to it, could delay the onset of these compressibility effects. The Messerschmitt Me 262, which first flew in July 1942, incorporated swept wings in a design that looked like it came from a different era. Test pilots reported performance that seemed almost impossible. Maximum speed over 500 miles per hour, a rate of climb that allowed the aircraft to zoom past defending fighters, and heavy armament that could destroy a bomber with a brief burst. When it worked properly, the Me 262 was untouchable by any Allied fighter. The problem was the phrase, "when it worked properly." Jet engines in the early 1940s were temperamental, unreliable devices with service lives measured in dozens of hours rather than hundreds. The Junkers Jumo engines that powered the Me 262 were prone to flameouts, compressor failures, and catastrophic turbine blade failures. Pilots had to manage throttle movements with extreme care. Rapid throttle changes could cause the engine to flame out or even explode. Landing and takeoff, when the aircraft was slow and vulnerable, were particularly dangerous. Allied fighters learned to patrol near known Me-262 bases, waiting to bounce the jets when they were at their most vulnerable. Hitler's interference made things worse. When shown the Me-262, he became fixated on using it as a bomber rather than a fighter. Despite desperate protests from Luftwaffe commanders who recognized that the aircraft's speed and armament made it ideal for destroying Allied bomber formations, Hitler insisted on bomber variants. This decision delayed the Me-262's deployment and ensured that when it finally reached combat squadrons in late 1944, it was too little and too late to affect the war's outcome. Other German innovations showed similar patterns of brilliance undermined by practical problems or poor strategic decisions. The Arado R-234, the world's first jet bomber, was a remarkable technical achievement that came too late and in too few numbers to matter. The Heinkel He-162, a lightweight jet fighter designed to be built by semi-skilled labor and flown by minimally trained pilots, was a desperate gamble that produced an aircraft so dangerous to fly that it killed almost as many German pilots as Allied ones. The Buchenbau 349 Natter, a rocket-powered interceptor that was launched vertically and intended to be partially reusable, represented innovation driven to the point of absurdity. Britain and America also pursued jet technology, learning from intelligence about German programs. The British Gloucester Meteor entered service in mid-1944, roughly concurrent with the Me-262. The Meteor used straight wings rather than swept ones, a conservative choice that limited its top speed, but made it more forgiving to fly and easier to manufacture. The American P-80 Shooting Star, designed by Kelly Johnson in just 143 days, also featured straight wings and came too late to see combat in the European theater. The contrast between Allied and German approaches to innovation was striking. German engineers, operating under a totalitarian regime desperate for wonder weapons, pursued radical solutions to the point of impracticality. Allied engineers, working within democratic systems where resources had to be justified and practical results demanded, tended toward more conservative innovations that could be produced in quantity and used by average pilots. Neither approach was inherently superior, but in the context of the Second World War, the Allied method of incremental improvement on sound basic designs proved more effective than German attempts at revolutionary leaps. The swept wing, Germany's most significant aerodynamic innovation, would ironically have its greatest impact after the war. When Allied forces captured German research facilities in 1945, they found wind tunnels, research papers, and experimental aircraft that were years ahead of equivalent Allied work. This data was quickly absorbed by American and Soviet designers, appearing in the next generation of jet fighters that emerged in the late 1940s. The North American F-86 Sabre and the Soviet MiG-15, the dominant fighters of the Korean War, both owed their swept-wing designs to captured German research. As the Second World War ground toward its conclusion in 1945, the aerial battlefield bore little resemblance to what it had been in 1939. Hundreds of thousands of aircraft had been built, millions of aircrew trained, entire cities turned into factories producing nothing but wings, engines, and weapons. The industrial capacity that America brought to bear was staggering, producing fighters and bombers in numbers that would have seemed impossible just years earlier. Britain, despite being much smaller and enduring years of bombing, had kept pace with remarkable production achievements. The Spitfire's production run told this story in numbers. From the first production aircraft delivered in 1938 to the last ones built in 1948, over 20,000 Spitfires were manufactured in dozens of variants. The elliptical wing that had seemed so impractical for mass production had been built 20,000 times by workers who became so skilled that production time per aircraft decreased, even as complexity increased. The final variants, powered by 2,000 horsepower Griffin engines, and capable of speeds over 450 miles per hour, bore little external resemblance to the elegant prototype that had first flown in 1936, yet they still carried Mitchell's distinctive wings. The P-38 Lightning's production exceeded 10,000 aircraft, serving in every theater of the war, and in roles from high-altitude interception to photo reconnaissance to night fighting. Kelly Johnson's supposedly impractical twin-engine design had proved adaptable and robust, capable of absorbing battle damage that would have destroyed single-engine fighters and bringing pilots home across vast expanses of Pacific Ocean, where a single-engine failure meant almost certain death. But the numbers only told part of the story. The real legacy of these revolutionary designs lay in what they taught about innovation, risk, and the courage to challenge conventional wisdom. Mitchell's elliptical wing and Johnson's twin-boom layout had both faced dismissal from experts who understood all the reasons why these ideas wouldn't work. Yet both men had persisted, driven by conviction that their calculations were correct and their visions achievable. The lesson extended beyond aircraft design. Every major innovation of the war, from radar to the proximity fuse to the atomic bomb, faced similar skepticism. Experts explained patiently why these things couldn't work, or couldn't be built in time to matter, or would cost too much for too little benefit. The successful innovations were those backed by individuals or organizations willing to push past that skepticism, to invest resources and careers in ideas that seemed ridiculous to conventional thinking. This pattern has repeated throughout technological history. The jet engine, which revolutionized post-war aviation, was dismissed as impractical for years before the urgency of war forced its development. The transistor, which would enable the computer revolution, was initially seen as inferior to vacuum tubes for most applications. The Internet began as a Defense Department project that many considered an expensive solution looking for a problem. Revolutionary innovations almost always seem ridiculous, until suddenly they seem inevitable. The Second World War was won by many factors: industrial capacity, intelligence, leadership, and the courage of millions of individuals who fought and died. But it was also won by engineers who dared to draw wings in shapes that everyone said were impossible, who proposed aircraft configurations that violated every rule, who calculated that the impossible was merely the very difficult, waiting for someone brave enough to attempt it. Mitchell died without seeing his Spitfire save Britain, but his elliptical wings flew over every battlefield of the European war, a testament to the power of innovation pursued with conviction. In the years after the war, as the world settled into an uneasy peace that would soon become the Cold War, the surviving pioneers of aviation innovation found their work taking new directions. Kelly Johnson went on to design the U-2 spy plane and the SR-71 Blackbird, aircraft that pushed technological boundaries as aggressively as the P-38 had. The engineers who had struggled to mass-produce elliptical wings found themselves applying those hard-won skills to building the first generation of jet airliners. German scientists and engineers, their country in ruins, were recruited by both America and the Soviet Union to continue the work on swept wings and advanced propulsion that had begun in the desperate final years of Nazi Germany. The aircraft themselves had varied fates. Many Spitfires and P-38s were scrapped immediately after the war, their military utility ended and their airframes worn out by years of hard service. Others found second lives, sold to smaller nations building their first air forces, converted to civilian racing aircraft, or preserved in museums. A few remained flying into the 21st century, maintained by devoted enthusiasts who recognized these aircraft as something more than just machines. They were monuments to human ingenuity and courage. Today, when a preserved Spitfire takes to the air at an air show, its distinctive elliptical wings immediately recognizable, spectators are watching more than just an old aeroplane. They're seeing the physical embodiment of an idea that almost everyone said would fail, that was too complex, too expensive, too risky. Those wings saved Britain when survival seemed impossible, proved that innovation could triumph over conventional wisdom, and established a truth that extends far beyond aviation. The impossible is simply the inevitable waiting for someone brave enough to try. The story of Mitchell's elliptical wing and Johnson's twin-boom fighter, of swept wings and jet engines, of all the ridiculous ideas that became war-winning innovations, teaches us that progress requires more than just intelligence and resources. It requires the courage to challenge established thinking, the persistence to continue when experts say you're wrong, and the vision to see possibilities that others dismiss as fantasies. In 1936, elliptical wings were ridiculous. By 1940, they were saving the free world. That transformation, from ridiculous to essential, is the story not just of the Second World War, but of human progress itself.